Happy Tuesday. We're going to finally finish up with vectors today. Of course, means your first test will also be available today. Discuss that at the end. We conclude our study of vectors, of course, with physics, specifically motion in space. You are familiar with position vector, velocity vector, acceleration vector. Velocity is the derivative of position. Acceleration is the second derivative of position or the derivative of velocity, right? It's rate of change. There's a little trivia. Does anyone know what the derivative of acceleration is? It's called the jerk. It's I've never studied it, and I was a physics major. So I don't really think it's actually useful at all. It's probably just something that they said, we're bored, let's come up with a name for it. Then there is a rate of change of the jerk, the derivative of the jerk. Called the snap. Rate of change of snap. The crackle. Rate of change of the crackle. It's the pop. Oh, I'm not kidding, but that's actually a thing. When last I checked, there was nothing named after the pop. And apparently they've decided to name things before position. Right? Because if you take the antiderivative of acceleration, you get velocity, right? And the antiderivative of velocity is position. So it makes sense you should be able to take antiderivative of position. And they've named the first several of those as well. Again, never used in physics. I studied physics for years. I have no idea how useful they are, but they exist. And so it's one of those Jeopardy type knowledge. What we're going to focus on for the most part is projectile motion and circular motion. Specifically, if you're going around a curve. All right. So when you go around a curve, you have two components of acceleration. You have the tangential acceleration, which is in the direction of motion. And then you have the centripetal acceleration, which is always toward the center of the curve. Right, so it's perpendicular to direction of motion. Now remember, velocity is a vector. If you studied physics 1, you should know this. How many accelerators are in your typical car? Remember, accelerator is a change in velocity. Say 1, what is it?
Not really sure.
Introductory mechanics didn't do a good job. There are three. You have the accelerator, the gas pedal. You have the decelerator, your brakes. And your steering wheel. Steering changes direction. Velocity has magnitude and direction. So even if your speed stays the same, you change direction, you have a change in velocity. Hence, you have acceleration. Right? Centrifugal force exerted by a moving particle of weight W at a point, and its path is given by they look different on my two screens. Okay. F equals W over G times AN. Right, so centrifugal force is weight divided by acceleration due to gravity, that's little g. All times the normal component of acceleration. Find the centrifugal force exerted by a particle weighing 5 pounds at the ends of the major and minor axes as it traverses the elliptical path, 20 cosine t, 15 sine t. That should be where the magnitude of r is measured in feet. Well, I'm going to need a few things. I'm going to rewrite R. We're going to need velocity. We're going to need acceleration. Now, again, velocity is just rate of change of position. Acceleration is a rate of change of velocity. We know the weight to be 5 pounds. What is little g going to be? What is it?
32.
We just use 32, typically as an approximation. Right, 32 feet per second per second. Notice we're just trying now to find AN, which is why we needed V and A. The normal component of acceleration magnitude of V cross A divided by magnitude of V. And so V cross A observation makes this really simple. It's strictly in the Z direction. Right, because both velocity and acceleration are strictly in the XY plane. Twenty times 15. 300, right? So be 300 sine squared minus negative 300 cosine squared. That makes the magnitude easy. It's just 300. So normal component of acceleration at any given time t, given by 300, over the magnitude of v. Form sine squared, square root of 400 sine squared plus 225 cosine squared. Right? But notice what it's asking. We want to know centrifugal force at the ends of the elliptical path. What value of t? What values of t give us the end of the major axes? Uh-oh. What is the major axis of an ellipse? Oh dear. Good enough for government work. Major axis. The axis on which the ellipse is longer, or its longest. In this case, the x-axis would be the major axis. The endpoint is called the semi-major. Then obviously your minor axis would be the other axis, the perpendicular axis. Right, or the axis which is the shortest, the radius is shortest. In this case, the y. And those points are the semi-minor. You should easily look at this parameterization, tell it is an ellipse centered at the origin, whose semi-major is 20, semi-minor is 15. The major axis is horizontal. So we want the endpoints. We want the semi-majors. Aren't the angles 0 and pi the endpoints on the x-axis? Notice what happens in each case.
That is just this.
Right. Notice what happens in both cases. Sine of both 0 and pi is 0, isn't it? Cosine of 0 and pi would be plus or minus 1, but we're squaring it, which will always give us positive 1. So the normal component of acceleration on both endpoints are the same. $300 over the square root of 225. That's 300 over 50. I should specify units. Feet per second per second. Where square root of 225 is 15. So 300 over 15. 20, right? 2 times 15 is 30, times 10 is 300. So the centrifugal force at those endpoints are going to be identical. Right? It's weight over little g times normal component of acceleration. $100 over 32. 25 over 8, right? And what are the units?
Why do you doing okay, 0 and pi? Why was it just 225 under that?
What is the sine of 0? What's the sine of pi? So the sine just disappears. What's cosine of 0? What's cosine of pi? Not cosine of pi is not 1.
Well,
Cosine of pi is -1, right? But you're squaring it, which is why both are 1. What about the minor axes? What's the ends of the minor axis? Be pi over 2 and 3 pi over 2, wouldn't it? Bless you. Similar argument. Shows that the centripetal acceleration at those two endpoints are also going to be identical, right? Cosine at both of those points is 0. Sine squared at both of those points will be 1. Be 300 over root 400 feet per second, right? Which is 300 over 20, which is 15. So again, centrifugal force at both of those points are going to be identical. Five times 15, 75. 75 over 32. Does not simplify. So it'd be 75 over 32 pounds. Find equation of projectile motion in rectangular coordinates written as y equals f of x. That's what we're going to start with. So first, equation for projectile motion. X naught, Y naught is its starting point, right? And V naught is initial speed or launch speed. theta is the angle it's launched at with respect to the horizontal. X naught, Y naught is starting position. Right, so X naught, it's X coordinate, Y naught, the Y coordinate. Now, typically speaking, when we look at projectile motion, we typically set the launch as the origin. Right, so that would make the equation this. And where in rare situations we might have an initial height. Right, but very rarely are we going to ever deal with an initial X coordinate. Right, so typically speaking, X naught is always 0. And rarely is Y naught anything but 0. So we're going to be working under the assumption that our launch point is the origin. We want to write this as a function y equals f of x. So first, solve the x component for t. Right, so we're going to write t as a function of x. Well, that's easy. T is x over v naught all times secant of theta. Now plug that into y equals v naught t sine of theta minus a half gt squared. That's now going to give us y equals f of x. Now v naught over v naught, that's nice. Secant times sine is what? Let's simplify this. Well, not technically simplifying. So write this as a function involving a single trig function instead of two different ones. Then secant squared, tan squared plus 1. And let's also write this as a single fraction. And say there's our function. So what we want to do in part B is find the range. Right? Range is the maximum horizontal distance covered. Well, maximum horizontal distance covered would be the time that the projectile launches to when it hits the ground, right? So we need to first find how long does it stay airborne. So we have to solve the y component for t. Specifically, when it equals 0. All right, now, here we're making an assumption I probably shouldn't make. And we're assuming that the launch point is the ground. I don't know if I should make that assumption. I will. You have to make an adjustment if it's not ground level. Multiplying both sides by -2, right? Then solving for t. Oh, we have to use quadratic formula. Oh, wait, what am I doing? I could have done this a lot simpler. Because c is 0. I can just factor out that t to make life easier. Which is exactly what we would get with quadratic. However, t equals 0 represents when the projectile is launched, right? So that we can ignore. So that is how long the projectile is airborne. Range is then just the horizontal distance covered during that time. And to just plug that t into the x component. However, we can make range look cleaner. Two times sine times cosine simplifies. Can anyone tell me what it simplifies to real quick? Bummer. It's the double angle formula for sine. That is the formula for range. Again, there has to be a slight adjustment if the launch point is not ground level. And then we were asked to find the maximum range. Well, there are two ways. You could increase speed. That's also going to increase the range. Well, that's boring. The other factor that would determine the range is the launch angle. Right. So increasing speed is always going to increase the range. So theoretically, be infinite. Now, practically, there is a maximum speed that you can reach, speed of light. You actually can't even hit the speed of light if it has mass. Right? You'd have to take a limit as it approaches the speed of light. But we're just going to assume, right, a constant speed. So we're assuming like it's a cannon. You can't really increase the speed at which it fires the cannonball. It's kind of a constant speed. So the only adjustment we really have to make is with respect to theta. And so we're going to make the assumption that V0 is a fixed value, i.e. we cannot change it. Then maximizing range involves finding the proper theta. Do you remember how to maximize a quantity? It was a minimum 2 semesters ago. You're not technically wrong with limit. Do you remember optimization in Calc 1? Right? Made use of several results. One of them being extrema occur only at the endpoints or critical points. We first need to find critical points. Finding critical points. What was a critical point? What do you mean change in direction? right? It's not technically direction, right?
It's just on the graph, it looks like that.
So I would agree that any time increase and decrease and decrease and increasing, you have a critical point, but not every critical point results in that. What are you gonna say?
Is any point that passes through the x-axis.
Where what passes through the x-axis?
Like when they I don't know, let's say like that's
You're not completely wrong.
well, I'm just saying at the point when the line crosses through. Like the point on the x-axis.
So you're saying that whenever the line crosses an x-axis, that's a critical point of the line? That is incorrect.
Like the derivative of it, so for this.
Right. And again, it doesn't have to pass through the x-axis. Touches the x-axis also works. Which is, of course, when the derivative is 0, but that's only half of it. Or when the derivative is undefined. So critical points are points where the derivative is either 0 or undefined. Right? So we take the derivative of range with respect to theta, because we're assuming that initial speed is a fixed value. Well, that should make this very easy. What's the derivative of our range with respect to theta? Yes. You forgot something. Yeah. You forgot chain rule. Well, clearly that derivative is defined everywhere. Right? Because cosine is defined for all real numbers. So now we just set it equal to 0 and solve. Means cosine of 2 theta is equal to 0. For what angles is cosine equal to 0? There's only 2 of them.
It's like.
I know what you're getting at, but it's not K. Right? It's not multiples of pi over 2, because that would include 0, pi, odd multiples of pi over 2. So 2K, so 2K plus 1 pi over 2. I'm going to use n just because that's what I'm used to. Right, so all odd multiples of pi over 2, which would mean that theta would have to be odd multiples of pi over 4. That's an infinite number of critical points. However, we're ignoring one important fact. Theta can't be any value. Right? Theta actually has a restriction on it. Not mathematically, physically. Can't theta only go 0 to pi over 2? Right? 0 would be a straight horizontal launch. Pi over 2 would be a straight vertical launch. Upwards. Anything else doesn't make sense. That gives us only one critical value, pi over 4. Sub C, just to represent critical point versus. We now need to determine if this is a max or a min. Second derivative test will tell us if it's a max or a min, local. There is a corollary to the second derivative test, which states if it is the only critical point in your domain, then not only does it give you a local extrema, it is an absolute extrema. So if the second derivative test here tells us it's a local max, it is the absolute max, because this is the only critical point in our domain. So take the second derivative. Well, 4v naught squared over g is always positive. Sine of 2 times pi over 4 is also positive. That makes the second derivative at pi over 4 negative. Second derivative test tells us that this results in a max. So to maximize range, you set the launch angle to be pi over 4. So maximum range, we said range was what? V naught squared sine of 2 theta over g. Maximum range is just V naught squared over G. Totally projectile is launched at a speed of 500 feet per second at an angle of 45 degrees to the horizontal. You're asked to determine the speed and direction of the projectile after 5 seconds in flight. First, let's write out the equation of motion. Cosine of 45 degrees, 2 over 2, right? Sine of 45 is the same. What is the magnitude of R being measured in? So what are the units? R represents position. Just feet. All right, so units for each coordinate is feet. And that's what this is saying. So determine speed. Speed is just what? The magnitude of velocity, right? So we have two ways to proceed. We can either find the velocity vector at 5 seconds, then take its magnitude, or we can find the speed function at any time t and then evaluate that at 5 seconds. They both give you the same answer. Either way, we're going to need velocity. It would be easier by just plugging in 5 here and then find its magnitude. And right now I'm going to specify, of course, that the magnitude of V is measured in feet per second. We can factor out a 5 to make this easier. Be what, 50 root 2? $50 squared is 2,500 times 2, right? Because root 2, excuse me, root 2 squared is 2. Right. So again, 5,000 minus 100G root 2. $10,000 minus 100G square root of 2 plus G squared feet per second. If this was a physics course, this is how we would leave it. Should say if this was a theoretical physics course, this is how we would leave it. Right, but that by itself doesn't really give you any kind of idea of what the speed is. So now plug in G as approximately what? We're in feet, so 32 feet per second per second. Should get about 403 feet per second, obviously. Direction will be given by tangent of psi is 250 root 2 minus 5G over 250 root 2. And you just take the y component of the velocity at 5 seconds divided by the x component of velocity. The angle. Right, that's the direction. Which of course can be simplified, right? We can factor out the 5 and get 50 root 2 minus g over 50 root 2. Right now, again, psi can only practically be between 0 and pi over 2, which allows us to take the inverse tangent. Again, theoretical physics, that's exactly how we would leave it. If you use the approximation for g, winds up being about 28.7 degrees. There's one more problem with motion to deal with. I'm going to be extremely generous and thus push the test off until Thursday. Also, here's a hint for the quiz that will be on Thursday, which will be on motion. Watch the video, because it is something that's in the video, but not something we're going to cover in class. So there will also then be a quiz Friday, which will be on new stuff, multivariate functions. See you all Thursday.